And let me remove this. Yes. How are you today? Good. Good. Let's get started. So today the ambition is to talk about fundamentals. Yes. And actually, so I hope for some interactivity since you're already, more experienced than me in some areas. So we will be talking about fundamentals of AI and ML, right? So to begin with, just to create some context. So we talk about, so in the context of artificial intelligence, we are talking about a system that kind of interfaces well, in a bidirectional way an environment. And then it possesses lots of kind of properties. I mean, this system to become truly intelligent. But the first thing it should be, I mean, its functionality is autonomous. So it should adapt. So its behavior is modulated by the environment. And actually, so now, so this bubble over here. So let's call it AI. So that's the intelligent creature that we are about to create. And if you ask me, so a great deal about AI is actually the reasoning. So knowledge representation and reasoning. So basically, conceptualization of what is perceived through the sensors and deriving facts, new facts based on existing facts. So that's what makes this stuff intelligent. But then again, so the fundamental problem is really the grounding here. So so this concept that we are operating with I mean, for inference / reasoning, so they need to be connected. So they need to have one-to-one correspondence to the observed phenomenon. And so, and then we have the actually the phenomena that we observe through some kind of sensor. So these are physical devices. Well, sensors here, and the actuators on the other side. And with help of sensors, we sample specific phenomenon, and we describe it through a set of characteristics. In other words, features. So and One question to you. I mean, to which extent learning is really must have in converting sensory input to features?
Can you rephrase it?
I mean, sensory input. So the raw signal. So I mean, it's a raw signal. It's not features, right? So you need to derive certain kind of characteristic properties. So the features. So what is the role of learning? Can you get away with it, or can you derive features without learning?
I mean, you can consider a value a feature, but it doesn't mean that it's learning. Is that what you mean?
Say again?
You have a raw signal, and that can be your own value. You decide I'm gonna put this, I'm gonna transform it into a float, for example, float 64 bits forever, and that's a value. That can be considered a feature.
I give you an example. So you have an accelerometer, no, say magnetometer. You place it on the road pavement, so on the asphalt, and then measures the and start to measure the change in magnetic fields when car is passing by. And so for your reasoning, you just need a binary, basically indication where there was a car or there wasn't a car. So how would you? So that would be your high level feature. So there was a car observed.
And then you're asking like what to do with the information from the magnetometer in order to detect. I guess you have a baseline that is the value that
exactly.
at the time.
Yeah, in some cases you can get away with very simple methods, but the important point. So I'm still talking about this connection. So the connection from the kind of perception system to the higher level of abstractions. In some cases, so I mean, this is easy to do. In some other cases, so you need some extra processing, I'll call it learning, to actually crystallize or to derive the features. So here we have the feature learning domain, and yes, and within this and currently, so basically this domain itself, so it can be considered disregarding the higher level reasoning. So and then so just to solve some particular task. And then then turns this set of methods into a set of machine learning methods, as per my authentic definition, if you wish. So when considered in isolation, obviously. And then obviously you may have different algorithms to process this inputs and for solving specific task. And normally to achieve same goal, you may use different approaches. So starting from this perspective, so let us think about the landscape of different methods to begin with. So if we talk about this ML, so just to kind of to simplify the task, so let's consider two branches. So we have the case with say simple, well defined features. And then we have complex features, or basically an input with no obvious structure in it.
Again,
Yes.
can you give an example for each case, like just a simple example?
Yeah, sure. So well, starting from the case below, so that would be that would be visual inputs or audio inputs.
Yeah.
So that's kind of very typical examples. The second case would be the case for manually extracted features. So crafted, so engineered features, or yeah, actually that would be the more general definition. So that class that we were talking about with, for example, detecting the deviation from the floor signal, so or you know, computing min max and stuff like that. So basic statistics on portion of a signal. So that's basically would qualify as simple features. So and so here we have set of methods. Which collectively we can call like classical ML. So and in classical ML, so we have again so depending on the task. So we may have the case of supervised learning. So where the ground truth is available, unsupervised learning. And obviously reinforcement. Just different strategies. So here again, so what I think is important to mention is a class of classical models for supervised case. So like SVMs. Well, again, so my favorite KNN as the first, the simplest memory-based classifier, and well, decision trees would be very successful and widely used algorithms. So just to as a kind of you know, a short deviation from this description, I have quite good contact to a local company. I mean, previously it was known as BehavioSec. I don't know if I told about it during the last course, but BehavioSec focusing on behavioral biometrics. So basically, their business case is to use the data on how you interact with electronic devices for identification purposes. So the way how you move your mouse, the way how you browse the internet, the way how you type. So all this uniquely identify you as you. And by the way, it's a very successful, it's quite a success story for LTU. So it's LTU-based company, and it was recently acquired by a large risk risk management, global risk management corporation. But so the bottom line is that, so I was asking, so what kind of methods do you use so to, I mean, in your products? And they, I mean, their ultimate answer was that we use, in 90%, 99% of cases, we use classical methods of machine learning. We use feature engineering and classical methods because, yes.
What do you mean when you say feature engineering? Do you mean that you try to preprocess enough for the classical methods?
Yeah, so to extract as many properties as you can. I mean, from a given use case, so to say. To give you an example, so for so I was collaborating with we had a joint project on processing of biomedical signals, and we were working with analysis of electrocardiograms. And so every year they have a computing challenge in cardiology. I mean, the challenge is different, I mean, from year to year. But one of the challenges was to, for example, to detect different kinds of arrhythmia, I mean, heart disease, by analysis of short recordings, ECG recordings. And I think the winning team, so there were solutions based on neural nets, etc., etc. The winning team basically used, or the winning solution was based on feature engineering. So they extracted, if I'm not mistaken, 117 features. So basically analyzing, so the simple feature engineering method is, for example, so you slide a signal with a window and then compute minimum maximum, but they also include high level statistics, and then so basically so altogether like 117, I said, features. So this part is very important. So prediction branch here is or regression. So you shouldn't forget about methods of linear, polynomial, reach, regressions. In your last lab, when you will be working with shallow neural networks, which is echo-state network, so I will come out. So the shallow neural network will appear here somewhere. So randomly connected recurrent neural network, shallow recurrent neural network. The learning there is done by regression. That's kind of
αυτά τα έβλεπε και στις Χάγιας στο τέτοιο. Έχουν πολύ χαμηλή ανάλυση. Δηλαδή, τέλος πάντων, εντάξει.
Yeah, I didn't want to listen what's going on there. Yeah, so this method is used as a learning, I mean, as part of the learning. So what you learn is the matrix of mapping, so of the state of a neural network to a label. So, and it is formulated as a regression problem. I will try to draw what I would call a generic architecture. It's nothing that would come to you as a surprise, but to me, this is something that unites all the methods. So there is, in my understanding and eyes, there is no. There are no fundamental differences between these methods that's regarded as ML and the methods of like deep learning that is currently proposed as AI. But nevertheless, so reinforcement learning. So here we have some Q learning. So I will not go into details. So learn. And well, some genetic stuff. So unsupervised method. So that is needed to be remembered. You told me some of you told me that you used it in one of the course. So PCA. So not to forget. So PCA is a valid method to use for reducing dimensionality, even in the context of neural networks. So not all dimensions are equally important. So in this case, SVD does the same job, and there's some more. But there is a set of methods of which are dedicated to data visualization, like t-SNE. They're also part of unsupervised learning. So it's again, so t-SNE. How many of you did use t-SNE for data visualization? Great. So this half is used. So ask them on this other side. Actually, it's that's a super important part in machine learning. So to have some visual understanding of your data. So and as soon as it gives you better feeling about the phenomena that you are tackling, and so t-SNE does a good job in this way. Yes, manifold learning techniques. So that's something is also present here. So nice. Yes, of course. So another thing which is very important, clustering. Clustering, that's also part of the a very important mechanism. And so part of this method, so normally they are not regarded really as learning, also they are, they learn statistical dependencies, basically. So they used heavily nowadays, and more nowadays, even for understanding of the processes happening inside neural network architectures. And talking about them, so in the case where you're either unable to extract features, or you are not sure, so in many cases, or there are definitely many cases where you do not see obvious structure in the signal. So then you can think of applying artificial neural networks. But even in this case, so you have rather large landscape of available techniques. So one of the, I mean, the most popular ones are obviously CNNs, MLP, or MLP is the first one. So for vectorized data, for more for sequential data and time series. So that's for vectorized data. For time series, sequences in general. So you have set of architectures like LSTMs, and even this. So as a deep, so this is a sample example of a deep architecture, or again, so that you have learned in the other courses. I think there is a great deal of studying a shallow architecture, so like echo state networks. Echo state networks, so ESN, so it's shallow recurrent neural network where rich regression is used as the last mile for the last mile classifier. And then obviously here we do have unsupervised case as well. And so here we have self-organizing maps, elastic maps. So they are known under different names, elastic maps and such, as well as so that way will or you will play with in this course, and the autoencoders. So in a way, it's also unsupervised. So the point with SOMs is to, well, apparently it's neural network architecture, again, a shallow neural net architecture, which is equivalent to dimensionality reduction techniques, classical dimensionality reduction techniques. Autoencoder as well, the feature extracting neural nets. But yeah, did I forget anything important? Huh?
Artificial curiosity under unsupervised.
Say again?
Artificial curiosity.
Artificial curiosity, that's something new for me. What is that? Huh? No, but seriously.
Well, it's like reinforcement learning, but it basically sets its own
Interesting.
its own what's it called points.
Interesting.
The rewards, yeah, rewards.
Oh, okay, interesting. Let me highlight it for myself to read more. I mean, you hardly can know all methods, or does you understand? I guess, but yeah. So, but what is important again is to have this understanding and be able to use this variety of functionality in a kind of unique and flexible way to achieve certain goal. So, for example, one of the threads, currently are to use methods or kernel methods, kernelized learning methods like SVMs, or the idea of kernels from SVMs, to explain functionality of neural networks. So so now it's really a time in the research domain. So if you're not focusing on kind of applied tasks, so basically to achieve higher accuracy on data set A, and then you try to tweak a model or select parameters of that model. So, but if you're interested in really kind of internals of algorithms, then you will see resurrection sort of research on manifold learning in context of deep neural network architecture. So basically trying to describe, to me, and that's partially what I'm doing in my research. So the data that you have, I mean, so that you describe, well, you either describe it through engineered features, or you just have raw features. They are kind of cloud points or point clouds in many dimensional space. And if you think about it, it's really fascinating to try understanding to understand a structure in this high dimensional space. So and for that, I mean, you really need to go and understand the processes inside various algorithms, and normally you do it by combination of methods. But listen, so what I want is to convey the following. When MEDDEC comes, at least for to but again, so like a generic ML approach. And this generic ML approach, that's what I will draw now. So that normally you see in the context of deep neural network. So you have your input features. These are your then again, in all the approaches, most likely in one way or another, you have an encoder block. So it's very so in convolutional neural networks in LSTM, so in CNNs, for example, these are the convolutional layers that do the job. In LSTM, this is the LSTM itself. But then, I mean, so here, what you get, you get representations, transformed representations, so modified representations, and this is a needed step. And we will be talking about this in the context of well, kernel methods and SVM during the next class. But this raw features in many cases, or in general, you should assume very bad separability. So it's a very and when I say that, so I mean, you can remain on level of definitions, of course, but what I want to convey is really a vision, internal vision of features as a multidimensional surface, and this surface, this manifold, so it has a very complex structure. And separability means that in this complex structure, it's hard to basically dissect. It's hard to dissect this shape in such way that you separate one category from another in a kind of straightforward manner. So this is the concept of separability. And so, as I said, in many practical cases, so this raw input data, and even you know, the features that you extract, so they are not strictly speaking separable, or not linearly separable. And as much as possible, so you want to transform these initial representations into some other representations which have better separability properties. And the way how you do that is different depending on the technique that you use. As I said, in CNN, so that you do it by learning of tons of parameters in the convolutional part of the network. But you can do it in other ways. For example, so there are techniques of expanding, for feature expanding. Again, so maybe I will not go into details of it, but at least so that you heard about it, like random Fourier features. I don't know. Did you hear about
Random
Fourier features? Yeah, but again, so I'm talking about this encoder block. So basically what it does, so it does a transformation of the original representation that you either construct by some expert knowledge, or you just use raw measurements, into representations with some desired properties with respect to their kind of separability in space. And so that is what I want to kind of seed in your mind. So even in classical machine learning, so this encoder part is done differently, obviously, so from neural networks. So there are explicit feature transformations. So one of the examples I will show you next time is that. So this is a very typical example for the kernel trick. So if you have data with two classes in a 2D scenario, so with the feature 1, feature 2, and one class is within the other class. So so when I say feature expansion, so the explicit feature expansion is a transformation of this 2D case to a larger dimensionality case. And in this very case, again, so I will show you properties. So it's enough to have a second order interaction between features. So where you transform 2D case to 3D case, so you introduce squares as a third feature. And then suddenly this middle points in the middle, so they end up in different parts of the paraboloid. But again, so that is a toy example. The thing is that here is a little bit of paradoxical thing, I would say. Yesterday, so we talked about this curse of dimensionality, right? So curse of dimensionality is I think you mentioned it. So it's about number of points that you need to sample to basically restore or correctly approximate given phenomenon. But there are in different contexts. So there is also a notion of blessing of dimensionality, where the data becomes more separable when expanding it. So expanding originally low-dimensional data into high-dimensional data. So it doesn't lead to exponentially a large growth of number of samples that you need, but it leads to better separability. And then there is this, well, I can, for those of you interested in math, there are a set of theorems, separability theorems that show that on high dimensions, like sufficiently high dimensions, like several thousands of dimensions. So in this high dimensional space, you can separate any point from all other points by a linear separator. So that's a kind of, I mean, these theorems, they are theoretical, so they don't, I mean, there are some extra steps to make it practical, but I mean, maybe during the break I can dig up the title. So it's interesting to read, believe me. But again, so one pretty much standard way for doing this encoder thingy in connection to classical machine learning methods is, for example, what I called random features. So so this method is an explicit way of producing representation that corresponds to certain kernels, and that's again, so the kernel is a very important notion in machine learning. Don't be stressed about kind of this concept. It's mainly, again, for your information, and I will give you some rationale behind it next time. But nevertheless, so again, the point is that this is a generic structure, and then so what you in principle want to work with all the time is this transformed features, no, transformed representations, better to say. Because on this level, in the same fashion as with the CNNs levels, we talk about so-called distributed representations. So call it embeddings. So the representation, and that's why I'm saying that you cannot say that certain position in this vector is a feature. So the whole vector is a feature. Is a feature. So it's a representation of a given phenomenon. But the important thing is that you take this representation, and here you can have multitude of downstream algorithms that actually implement certain or that help you to achieve certain tasks. So again, in CNN, so in classification, in the classification task, you use what? Multi-layer perceptron, fully connected layer. You can easily use whatever other technique. So you can put SVM, you can put rich regression, whatever here. But this is the level of modularity. So it's not kind of specific to deep architectures. Yeah, you can use regression to do some prediction, to solve some prediction. Yes. Let us make a short break before I talk about something different. Some couple of minutes like stretching. And I will try to find this title. Yeah. Ja, genau. Are we missing anybody? Shall we resume? All right, let's continue this verbal exercise, so to say. Yeah, I found this title. Actually, interestingly enough, so the author of this article is a professor from Leicester University in the UK. Who was actually my teacher back in Krasnoyarsk. So long time ago. When was it? Like middle of 1990s. Alexander Gorban. So he is one of the pioneering researchers in neuroinformatics and well, modern artificial intelligence. Oh. The title I mean is this one. Stochastic separation theorems, how geometry may help correct AI errors. And again, so maybe the math here is a bit, well, in this version is at least not that scary, I mean, from the first glance. But the bottom line, so again, so if you're interested in a way in this other aspect of high dimensionality, so the blessing part of it, so this is the place to read about it, and but moreover, this article is so suggests practical steps on how these theorems can help in correcting errors. So the idea is pretty much, I mean, the algorithmic idea is simple. So you have a neural network that does classification, and then it produces errors. So I mean, during the evaluation phase, and for each error, so you record, you do a snapshot of the neural activations. So, I mean, like, and in this way, you have this high dimensional representation of the occurrence, and then you try to separate. So you build a separate classifier, so to say, trying to reduce the number of errors, basically to isolate some specific error cases or groups of error cases. Yes. Where do I do record, right? Yes. Again, so now let's talk more practically about easy stuff. Again, it's very easy. So we talk about this simplest case, memory-based learning, just to we use it to assist us in the discussion about some basic definitions. So in this case, we have again a two-dimensional case, which is easy to visualize with say two features. And so by these two features, you describe like three categories. And then, I don't know, cats, the usual cats, dogs, and airplanes. Airplanes, right? And so the idea, so with there's the smart word for it. Discriminative, for creating discriminative model, which is classification, basically, is for a new point that you haven't observed before. So decide to which category it belongs to. So, and so we will use this case to basically refresh our knowledge about distances which are used throughout whatever machine learning algorithms. So distances. what kind of distances we may use to reason about it? Well, it's a geometrical approach. So I mean, AI, machine learning, so no rocket science, really. I mean, so at the end, so we just want to compare proximity in one way or another, or similarity according to a certain measure. And you need to define this measure. So what kind of measures we have for distance-based methods?
Euclidean.
Huh?
Euclidean.
Euclidean. So this is L2. That would be yes, this is no, let me spare some place above L2. Yes, right. So you basically compute this thing over here, which is sum of square roots of so feature I x minus feature I y square, or all i's, right? What else? Manhattan, L1, right? So Manhattan, I have I minus x module f I y, right? So something like that. Manhattan. Anything else? What about this one? Sum f x I minus f I y power p 1 over p. Huh? Yeah, it's a general case. It's a Minkowski distance. Yes, and so now since well, you're all familiar with it, what are the what kind of aspects these different measures capture? So why would you go for one measure over the other? So what differences in feature favor one or another measure? Well, the higher is p, the more sensitive this distance measure becomes to individual to the differences in the individual features. The smaller is p, so basically down to L1. So we capture many medium discrepancies, so it's more averaging. So if you want to kind of react on, you know, changes in individual features, drastic changes in individual features, so maybe the higher order of distance you would choose. On the other hand, so these are kind of distance or I don't even know what is the correct term for this, like a linear distance, so to say, or topological distance. There is another measure that is used in the context of machine learning, which is angular distance, right? What is the measure of the angular distance? So basically, instead of kind of computing this distance between 2 points, what you up to is so if now it became a little bit populated here. So if you have this minus over here and you have this square, and we have 1 minus over here. So if we represent it as a vector, and the second data point again as a vector, and so all others as a vector, like this one. So what we can do, we can compare the angles between these vectors. And then this is this introduces a very useful and very meaningful metric in the context of AI, meaningful really with respect to similarity. So it's a cosine similarity metric. So, which is defined as dot product fi x fi y divided by the norms of these two vectors x, so the whole of it, the product of norms. Just dot product is also used as a measure of proximity, as you see. So this is just a normalization, but this normalization makes it bounded between 0 and 1. So basically, you can say that I mean that's why it is called similarity measure. So closer to this measure closer to 1. And you say that two samples are more similar compared to cosine of 0 degrees, which is orthogonal, so dissimilar vectors. So very intuitive kind of measure. That is used. This measure is used heavily in NLP-related tasks in cognitive sciences. This measure is not normalized. It is used in support vector machines, as you will see next time. And that is the key to introduction of these kernels. We will discuss it again next time. But again, so these are the landscape of distances that you may, and not to mention, but that we will have a separate discussion about the distributional distance, like cross entropy, which is used in the context of the backpropagation algorithm. So then, so I have some amusing calculations in my opinion that is kind of very practically useful. Yes. What else? Yes. Right. Right. Maybe here, while still being here. partially or to some extent, this distance metrics that are used in, as I said, in virtually all algorithms of machine learning, so they place requirements or they demand that data comes in different in standardized form, or so the pre-processing is very important. So that's there are no kind of huge deviations in features. So that so just remembering that. So some measures are more sensitive to deviations in different features. So just not to make your decision biased to extreme values. So that's I mean that's why normalization is a kind of standard way of doing. While talking about normalization, a question to you: how would you do normalization? So now we talk about a machine learning context, meaning that we have a particular task to solve. It's database. So we want to create a data-driven model, and so you have this split on training and test set. So how do you do normalization? Yeah, it's not a very tricky, but it can be tricky. Yes, please.
I don't know if I'm mistaken, but I think it's like an operation where you take your feature x minus the mean divided by variance.
Yeah, but I mean, with respect to, so you do normalization per feature. So now you have your data. So you have your data that you want to build a model on, and then you split it into training, possibly validation, not necessarily, and necessarily testing set. So while still here, so normalization. So which data would you use for normalization?
I think we have this specific program on one course,
Mm-hmm.
and if I remember correctly, the idea was that you shouldn't normalize all of it, because by normalizing all of it, you had some information of training and testing.
Exactly. So that's a problem. So the practical problem of data leakage. And so you, I mean, in principle, but I mean, I always thought on this expression now. So it's not that kind of obvious nowadays. But yes, in general, you're correct. So this part should never be touched. So not touch. So you only do touch it for the evaluation. And if you do that, so one for normalization, so that's one of the in principle, so the risk of leaking some information into your model. Then again, so we live in the real world, and it was like as recently as, I don't know, when was it? Last week I talked to my colleague here. He said, but listen, so I work with this data set and I don't touch it, and I normalize it just for but then I check the testing set. So the data, I mean, for the same class, they're kind of well, I don't remember the exact percentage. So the values in features, they're way higher than the average. So the discrepancy is way higher than in both testing and validation sets. So meaning that so this data, so you will achieve really kind of you shouldn't expect really good results. So again, so the message here is that when saying do not touch doesn't mean do not pick at it. So you should understand your data. And understanding your data should place your correct expectations on the outcome. And then even it can shade some light on the performance of your classifier. Yes. By the way, so again, so now it's a question to you. So if you don't have enough data, so to split into these three sets, what are your strategies? Well, testing set exists. So if you don't have enough data to do this, kind of
transform the original samples.
Huh?
You transform the original samples to augment.
Okay, so you can augment the data sets, but can you still so if the data is very kind of small, so can you still do validation? What are the strategies there without augmentation?
Cross-validation.
Cross-validation, exactly. So cross-validation is the mechanism to remember. And so again, there are different strategies. So in the extreme cases, so this concept of leaving one out, and so that's kind of one of the valid concept. But again, so that's just a recapitulation of what you all know since previously. But since we started to talk about performance, so the effect on performance, so let's talk about or let me see. Oh, that's easy. Yes. Let me just quickly refresh your mind or your memory on the way how you do this evaluation. So it all started with, of course, you remember binary classification problem? Yeah, so of discriminative models. Binary classification. And in binary classification, so you have basically two classes, class 1 and class 2, and so they are normal given names. So like so one class is positive, another is negative. Yes, so P, N. And hence we have this notation of true positives. So T, P. So basically the outcomes which are predicted as true and are true. And false negatives. True negatives. And false positives. So, okay, so now remind me quickly. Yeah, and by the way, so just to be on the same page, so if we have a positive class and a negative class, so if we can construct this table, so again, we have positive, negative, so it will be like this: T, P, F, N, F, P, and T, N, right? So help me out completing this things. Accuracy. What is it?
Two positive. Or all the positive, two positive and one positive.
No, true positive and true negatives.
True negatives, yes. Divided by all of them.
All of them. Yes. Anything else? Any other performance measures that come to mind? Precision. Okay. So, have you been tortured on that? No. Do you dream about it? That's bad.
Recall.
Precision, recall, final recall, total recall. Yes, right. But precision, what is it?
It's true positives divided by all the positive states.
Yes. Yes. Recall. No. True positives.
True negative.
True positives plus false negatives. So basically, true positives divided by all all actual positives. Yes. Anything else? Did I miss anything? I did.
F1.
F1. What is F1?
I don't know.
I don't know. Okay. That's to recall multiply by precision. Precision divided by sum of this. Why do we need F1 score?
We need to see the accuracy of each class individually. Isn't not accurate, but we need to see how well you predicted each class individually.
Yeah, so this is mainly useful in unbalanced cases, right? And finally, so if you generalize it to multi-class case, so you have class 1, class 2, class n, class 1, class n. What is this class I? So this structure over here, what is it? The whole of it. Matrix, right? CM, very useful. So what is false false positives in this case? Well, true positive is obviously so class one is is class one. So, but what is interesting is false negatives. So false negatives is just is sum of all other values in the row for this class. So basically false positives. So that's the column. So, right? Yes. On that very kind of simple note, I think we end for today. So next time we will be talking about SVM mainly, so internals and kernel and formulation of the kernel problem. Yes. Thank you.